All right, so we continue to move in the direction of, more and more information, more and more things to kind of watch out for and be aware of. So before we get into electron configurations, which is our next topic, let's go back and review our topic from Monday, which was all about quantum numbers. And so to this end, I've got 5 sets of quantum numbers here on the board. The question is, which of these 5 sets are valid? And subsequently, which ones are invalid? Now, to answer those questions, what we have to think about are, in this case, not so much what do the numbers represent, but what are the possible allowed values of a quantum number given the other quantum numbers? So just as a starting point here, let's look at letter A. Now, letter A starts with a principal quantum number, n, of 1. Is that possible? Can we have a first energy level? Yeah, so that part's okay. If I'm in the first energy level, remember L gives us the orbitals, the sublevel shape. And L of 0 refers to an s orbital. Is there an s orbital in the first energy level? Yeah. So thus far, 2 for 2. Given this value of L, can the magnetic number be -1? It cannot. Remember, the magnetic quantum number is bounded by the angular momentum quantum number. That's why it's m sub L. That sub L is a clue as to what the allowed values for that number are. They go from -L to +L. If my L value is 0, -0 and +0 are the same thing. They're 0. So the only possible value for the magnetic quantum number in that circumstance would be 0. -1 would not be allowed. So combination A is not a valid combination. Let's go ahead and look at combination B. In combination B, our principal quantum number is 3. Is there a third energy level? Yes. Remember, any whole number is an allowed energy level. So that's fine. Our L value is 2. This would correspond to a D sublevel. Is the D sublevel allowed in the third energy level? Answer there again is yes. Remember the rules for L can go as high as n-1. So with n being 3, n-1 is 2. 2 is the maximum number for the angular momentum quantum number. So it still fits. M sub L, we're given a value of -2 here. Does that fit? Yeah. Remember, we're bounded by the L, -2 to +2. -2 is one of those allowed values. That one's okay as well. Spin quantum number, +1/2. Remember, there are 2 allowed values for the spin quantum number. The +1/2 and the -1/2. Spin up for positive, spin down for negative. So that's a allowed value as well. So B is a potential set of quantum numbers. What electron does it correspond to? Well, we actually need a little bit more information for that. But given that we're talking about a 3D orbital, we're talking about primarily something in the transition metals more than likely. So our best possible guess here would be that this electron is in scandium, but this could also be describing any of the electrons in a ground state for any element beyond scandium as well. All right, with these other three combinations, what I want you to do is kind of pick out the same things. Go through it step by step, use your allowed rules to quantify and pick out which combinations are good and which combinations are not. I'll give you a couple of minutes. All right, let's do a quick poll here. How many people think that C represents a valid set of numbers? Okay, a couple of you. For those of you that do not, point out one number that is wrong in C. All right, good. Okay, and Sebas, you're right, that's incorrect. Why can't M sub S be 0? Right, it's either going to be positive half or negative half. 0 is not one of the allowed values. So if one number is invalid, that invalidates the whole thing. Are there any other numbers that are invalid here? Yeah, Kelly? Okay. L equal to 2. It doesn't have to be n minus 1. It just has to be, that's the maximum that it can be. So L could only be 0 or 1 here. It could either be 2s or 2p. It can't be 2D. There is no 2D. All right. How many think that D represents a valid set of numbers? Okay, that's looking like most of you, and most of you would be correct here. Second energy level, L is less than or equal to n minus 1, so that's good. M sub L is no bigger than positive or negative L. Negative 1/2 is an allowed value. D is a good set. What about E? All right, what's wrong with E? All right, Ben.
They're all negative.
Well, some of them are allowed to be negative. So We can't just point to that. Which ones cannot be negative?
N and L.
N and L definitely cannot be negative. Those both have to be whole numbers. M sub L of -1, M sub S of -0.5. M sub S is actually a valid quantum number. M sub L could be a valid quantum number if L was 1 or greater. But since it's negative, yeah, the whole thing falls apart right from the start. There's no such thing as the -3rd energy level. Energy levels start at 1 and go to infinity. So we move from quantum numbers to electron configurations. Now, what's interesting about electron configurations is that electron configurations and quantum numbers kind of tell us the same thing. Electron configurations tell us where every single electron is in a given atom, in terms of where is it in terms of energy level, where is it in terms of sublevel. But instead of describing a single electron like a quantum number does, an electron configuration describes every electron and how they're distributed. So within an electron configuration, I could point to a single electron inside of that configuration and say, these are its 4 quantum numbers. And so we're going to use some of the same terminology, some of the same principles to describe electron configurations that we did for quantum numbers. But instead of applying it to a single electron, we're going to describe all of the electrons all at once. Now, when it comes to electron configurations, there are 2 guiding principles that we use. One of them is something called the Aufbau principle. The Aufbau principle is a filling principle. Basically says that electrons are going to start at low energy and go from lowest energy to highest energy. Kind of makes sense, right? The electrons are going to go where they are going to need the least amount of energy in order to exist. Otherwise, they've got to be constantly absorbing energy to maintain an excited state, to maintain those higher energy levels. And we know that that's not always possible. The second principle is something called Hund's rule. Now, Hund's rule comes about when we start to look at individual sublevels as opposed to energy levels. When we look at sublevels, the p sublevel, which has 3 orbitals in it, the d sublevel, which has 5 orbitals in it. When we look at those, we're going to apply Hund's rule. And Hund's rule says that all of those orbitals in that sublevel are all equivalent in terms of their energy. And with that equivalence, they're going to fill evenly. Why do they fill evenly? Well, we have to keep in mind, these are still electrons. They're negatively charged. And if I put 2 electrons in the same amount of space, they're going to repel each other naturally. Hund's rule separates them as much as possible for as long as possible and does not pair them up until we have no other space to separate them. And once we do, that's when we start to get into that spin up, spin down kind of configuration. Again, by convention, the spin up electron is generally considered to be the lower energy configuration. So when we draw orbital notation out and we're filling in those degenerate orbitals, we're going to fill them with spin up electrons first. Spin up electrons are easy to spot. They are arrows that are pointing up. Spin down electrons are also easy to spot. They are arrows that are pointing down. So those are our two guiding principles. Now, there are a lot of different ways of remembering the Aufbau principle. This is a common way. You can see this one is copyrighted by the Encyclopedia Britannica from 2007. And sadly, this diagram hasn't changed too much. This is actually a diagram that existed well before 2007 and is still highly in use now. If you follow it, you can see that we have our 7 energy levels that correspond with the 7 rows of the periodic table. And we can see every single energy level adds one new possible set of orbitals. Now, the reason we don't consider the 5G or the 6F or the 7H orbital or any of these light green ones here is primarily because, well, they're only in existence for excited states. A ground state electron never fills these. There's plenty of capacity in these orbitals listed that are much lower in energy, that those get filled well before any of these other ones. The 7p orbitals, the 7p sublevel, is much lower in energy than the 5G orbital is. And so these will fill first before these ones do. But you can see that if you draw it out in this way, and drawing out a series of diagonal lines, you can come up with the proper filling order for electrons using the Aufbau principle. Problem with this method is, well, it's kind of long. It's tedious. You got to draw this pyramid every single time you want to do an electron configuration. And the other problem with it is, well, it doesn't take too much into consideration as far as exceptions are concerned. You still got a lot of memorization to do. So we don't tend to use this one very much in my class because, well, frankly, there are better ways. As an illustration of Hund's rule, we get into something here called orbital notation. Orbital notation breaks each sublevel into its representative number of orbitals. So the S sublevel only has one orbital, so we just see it depicted as a single box or a single line. The P sublevel has 3 orbitals in it, so we see it depicted as 3 boxes or 3 kind of underscore lines. The D would have 5 boxes, the F would have 7 boxes because that's how many orbitals are in each of those sublevels. But you see, as far as filling is concerned, we see the Aufbau principle immediately in play. The 1s orbital always fills first. The 2s is the next lowest in energy, it fills next. And so we see this pairing take place here between lithium and beryllium. And then once we get to boron, now we see Hund's rule take over, where each electron fills a different orbital before we start to pair them up. And so oxygen would have an additional electron paired up here. Fluorine would have another one there, and then neon would have the entire sublevel filled that way. And then once we fill that, then we move on to the next sublevel, which would be the 3s, and then the 3p, and then the 4s, and so on, and so on, and so on. But again, orbital notation does some things for us. It does help us to pinpoint. It also helps us to do things like if I wanted to identify specific quantum numbers for specific electrons, I could do it in this way. Because, again, by convention here, for the P sublevel, for example, this first box, second box, third box, do have designated quantum numbers associated with them. We go from the negative extreme on the left to the positive extreme on the right. And so if I were to identify the quantum numbers for this electron, I could do so based on its position, based upon its direction. It would be n equals 2, L equals 1. That would represent the 2p sublevel that it's in. M sub L would be -1. M sub S would be +1/2. And that represents the orbital box, the leftmost orbital box, and its spin up direction. And so I could technically do that for any electron in an electron configuration by looking at its orbital notation. And it wouldn't take that long to do. It just takes a little bit of practice to kind of figure out how that designation goes. But you could very easily and quickly do that if you had the whole thing in front of you. But when it comes to electron configurations on the whole, where do we get these guys? How do we quickly come up with this kind of a configuration? And the answer to that question ultimately comes down to the periodic table. So if you have your periodic table on you, I encourage you to pull it out again. If you didn't bring it, find some way to write this down in some kind of manner, because the information that I'm going to present to you is going to help you massively in terms of figuring out how to quickly do electron configurations based upon position on the periodic table, as opposed to drawing some sort of funny pyramid or drawing out orbitals for everything and then trying to count out how many electrons there ultimately are. So one thing that you need to remember for configurations, first and foremost, helium is going to be over here for our purposes of electron configurations, because this whole block, starting from hydrogen and covering both the alkali metals and the alkaline earth metals, this is our S block. And the S block follows the energy level, the period number, exactly. So you should already have these numbers on your periodic table. If you don't, go ahead and put the period numbers in there. It's going to help a lot. But what this means is that if I'm looking straight across, the electrons in this block would represent this would be the 2s sublevel. We're in the S block, second energy level, 2s would be where they intersect. Down here, strontium, this would be in the 5s, fifth energy level, S block. So we're going to turn the periodic table almost into a map of sorts, where we can pick out coordinate directions and get an idea of, at the very least, the sublevel on which that last electron of that element resides. And once we figure out where the last electron is, we can kind of figure out all the rest of them, because we can make general assumptions that every sublevel before that last sublevel should already be full. So that's the S block. Over here on the right-hand side, starting with boron and going all the way down to oganesson, this is your P block. The P block also follows the period numbers exactly. So once again, if I'm looking at something like selenium here, selenium is in period 4 of the P block. The last electron in selenium would be in the 4p sublevel. Boron, boron is in the second period in the P block. It would be a 2p sublevel for its last electron. Moving onward. The transition metals going from scandium to Copernicum. This is the D block. Now, starting with the D block, things get a little bit funny because it's not the period number that we're looking at. It's actually going to be the period number -1. So if I look at something like palladium here, palladium is in the 5th period, but its last electron is actually in the 4d sublevel. 4d. We take the period number, we subtract 1 to get the sublevel that we're interested in. This is primarily to account for that energy gap difference. The fact that the 3d, the 4d, the 5d are all slightly higher in energy than the 4s, the 5s, the 6s, and so on. We're taking that into consideration, and so we've offset it by that little bit. This allows us to keep the proper order. Lastly, we've got our lanthanides and actinides here. This is the F block. And the F block is actually offset by 2. The F block starts in the 6th period and the 7th period. So the lanthanide series are actually represented by 4 F configurations. The actinides are actually 5 F configurations. Now, one word of note here, lanthanum and actinium, their actual position on the periodic table is somewhat debated. Some periodic tables will actually put lanthanum and actinium as elements number 57 and 89 here in the D block. Some will actually consider them the first of the F block and put lutetium and lawrencium numbers 71 and 103 in that D block instead. This level of ambiguity is one of the reasons why, as far as configurations are concerned, the only time we will see F block elements come into play is if we are buzzing through the F block to get to somewhere else. So if I need to do the electron configuration of gold, for example, gold, element number 79. Well, you can see there that on the way to gold, I'm going to have to go through this F block. And I'm just going to have to deal with the fact that there's a 4F14 in there because all of the F block is completely filled because we have to go through those elements to get to gold. That's the only thing we're going to work on from there. We're not going to ask you the configuration of curium or of dysprosium or of praseodymium or any of those because honestly, there are more exceptions than there are hard and fast rules inside of the intertransition metals. Way too complicated. And again, most of these elements I've never seen, touched, or looked at in my life. I have seen a little bit of uranium. We have some uranyl salts upstairs that I do a nuclear lab with one of my other classes with. That's it. Most of these other ones, they're rare. You're not going to see them. We're not going to spend our time going through them either. If it came time to go through and work on those, there's an upper division chemistry class that is just for you for that situation. This isn't that one though. So now that we've established this map, how do we actually use the map to do electron configurations? Well, the answer to that can only come by us doing some examples. And so what we're going to do, I'm going to be hopping back and forth a little bit here between the two. Ultimately, what we have to do is we identify the sublevel for the last electron. We identify which electron in that sublevel it is, and then we can kind of work backward, filling up all the sublevels that preceded it using the periodic table and using that map as a guide. So in our first example, we're looking for the electron configuration of zinc. Zinc, element number 30, we can see here is the anchor of the 3D sublevel. Again, if we mark up our periods here, zinc is in period 4 in the D block, so it's in the 3D sublevel. Our next task is to identify which electron it is. We do that by counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Zinc is the 10th element in that D block. So its last configuration is going to be 3D10. That's what it's going to end with. That gets us from here to here with regard to zinc. All of the other sublevels that preceded 3D10 are going to be completely filled. So now we just need to kind of go through and do the rest of those. So I have 1s. S sublevel has a capacity of 2, so it's 1s2. I've got 2s. S has a capacity of 2, so it's 2s2. I've got the 2p. P has a capacity of 6, so it's 2p6. Then 3s, 2, 3p6, and finally 4s, 2, before that 3d10. So there are a lot of ways that you can kind of go about doing this. But to me, it always helps to know where to stop. If I know where to stop, then I know that everything else before that I can just completely fill in. And I can use the periodic table as that guide. So if I forgot somewhere along the line that the P sublevel has 6 electrons in it, I can remind myself of that by counting. 1, 2, 3, 4, 5, 6. 6 electrons in that block, 6 elements in that block, 6 electrons in that sublevel. The periodic table allows me to turn this into a counting contest as opposed to a memorization contest. And anytime I can turn memorization into counting, I know I'm on better footing in the end. So that was the first one. We had to do zinc. Let's look at the next one. The next one on our list, argon. Argon, we're looking at right here. Argon is the anchor of the 3D, or excuse me, 3p block rather. We can see that argon is 1, 2, 3, 4, 5, 6 in that. So my last configuration is going to be 3p6. Again, I can go from the start, 1s2, 2s2, 2p6, 3s2, and then finally this last one was 3p6. 3p6 was my starting point or my stopping point. That's where I am there. I've got my configuration completely filled. Right. Any questions about either of those first two? Okay, the next one on the list was doing the orbital notation of scandium. Scandium, we looked at, is right here. Now for orbital notation, we're going to need to do the arrows and the bunches. So in that case, the only thing I want to really point out is that the 3D sublevel is where we're going to stop. So for orbital notation, I need to draw either a series of boxes or a series of underlines to represent those orbitals that precede it. And so drawn this way, this is almost like a chemical version of hangman. Again, scandium is our end point. So we know that everything else is going to be filled before we get to that end point. So we can just start filling it in with arrows. The arrows you use are completely up to you. Convention and non-convention both kind of agree. They can be double-headed arrows like this. You'll see also single-headed arrows like this. Both are considered to be acceptable. Neither one is considered to be more correct than the other. So it's really about personal preference and your level of confidence. But you're going to fill up all of the orbitals until you get to that 3D sublevel. 3D sublevel, now we need to look at scandium's position. Scandium is the first electron in that sublevel, so it is the only electron in that sublevel. And by convention, it is spin up and in that first slot. And so that's all that we needed to do. All right, any questions with regard to configuration so far? Okay, so one of the things that you might notice is that these kinds of configurations, full configurations, can get on the lengthy side, especially if we're doing orbital notation, or worse yet, we're doing any kind of element that has more than, say, 40 electrons in it. Configurations get longer and longer and longer. And the thing is, we know that most of those configurations have orbitals and energy levels and sublevels that are just completely filled, and there's no variation in them. So what do? One way is through a shortcut. This is called a noble gas configuration. What a noble gas configuration does is it accounts for all of that filled stuff and says, okay, if I go back to the nearest noble gas, I recognize that all of the electrons that make up that noble gas all come from completely filled sublevels. And now I can bracket that up, have an understanding that all of those electrons are there for that noble gas. And I can talk about what's different, what's unique, what makes this element different from other elements in the same period. And that's what it does. So as an example, we can look at calcium. The full electron configuration for calcium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. What the noble gas configuration recognizes is that this part of the configuration, these 18 electrons, can easily be represented by the 18 electrons of argon. There's no variation, there's no variability in them. Those 18 electrons are what we call core electrons. They don't react, they don't move, they don't really do much of anything other than occupy the lower energy levels. It's all the stuff in that outer energy level that ultimately reacts and gets excited and moves along. So this part of the configuration gets rewritten as that noble gas. And then all that we speak to after that noble gas is what is different. Now again, how do we get there? If you look at your periodic table, calcium was right here. We go backwards until we hit a noble gas. That noble gas is what we put in brackets. Then we finish the electron configuration that follows that noble gas. We don't go forwards because we have no way of showing the electrons that aren't present. The difference between krypton and calcium is 16 electrons. How do we show that those 16 electrons aren't there? We don't have a real good way of doing so. But if we go back to argon, argon has 2 fewer electrons, and we can share. We can say, okay, these are where those 2 electrons are. They're in the 4s orbital. So let's close out today by doing a couple of noble gas configuration problems, just to kind of put ourselves in the right direction. So we start with vanadium. Vanadium, element V. If I look at vanadium, vanadium is a transition metal, element number 23. If I go back from vanadium, I get to element number 18, argon. Argon, Ar. What's left after argon? I've got 4s2, and I've got 3d, and I count 1, 2, 3 for vanadium, 3d3. And that's it. There's a 5 electron difference between argon and vanadium, and we just said where those 5 electrons are. 2 of them are in the 4s, 3 of them are in the 3d. For arsenic, arsenic is element number 33. Again, I go backwards. From 33, I end up again at element number 18, argon. Now I need to fill in the rest. Argon is followed by 4s2, the entire 3D block, 3D10. And then arsenic is the third element in that P block, so it is 4P3. The difference between arsenic and argon is a 15 electron difference, and I've accounted for those 15 electrons, 2 in the S, 10 in the P, or excuse me, 10 in the D, and 3 in that 4P, that final configuration. Okay, so where we're going, I am going to extend the deadline for the electron configurations by a day. It'll be due Friday night because we have not talked about all of the exceptions. We have not talked about ions. Both of those are featured in that post lecture. So I don't want you to get burned by something that you haven't seen yet. But we will certainly talk about them first in Friday's lecture. And then we'll kind of carry it out from there and get ready for our review by talking about our last topic, periodic trends, on Friday. Have a good afternoon.